Hi. So thank you for the introduction and also thank you for the invitation to this conference. I'm very happy to join in and give some results then on which Deepak and Mustanze have some background. You've seen the outline already since a short talk. I'm not going through it. So let me just start what it's about. So, okay. So we are talking about dynamic universality classes. In particular, in one-dimensional systems, particle systems that interact and that have some short-range interaction. Now, we all know that we can observe unusual static properties in one dimension, unusual in the sense of not being captured by mean field or not being present in higher dimensions. So, for instance, there's anomalous transport in equilibrium steady states with divergent transport coefficients. And there's also phase separation, which you normally don't have in one dimension. So these are just static phenomena, which are very interesting and still not fully understood. But they're also dynamical phenomena, critical phenomena, which are non-diffusive and therefore also not so common. It's already been known for a long time that the super diffusive spatial temporal scaling in the context of the KPZ equation, this was discovered, and I think it was Deepak who made the first exact contribution by calculating the dynamic exponent of the asymmetric exclusion process, which is indeed 3/2, not diffusive. So in fact, since then, it has been discovered that there are many other dynamic universality classes with the dynamic exponent that's less than 2. And also the scaling functions that go with it are not Gaussian, but they exhibit scaling and universal scaling. So now what are the systems where these phenomena have been studied? Well, there are many kinds of systems. Two generic model systems that have been looked at a lot have certain local conservation laws like anharmonic chains, which have conserved energy, momentum, and other conserved quantities, or also very frequently studied, and this is also mostly my own work, lattice gas models. So you have particle hopping systems on a lattice, one-dimensional lattice, where you have different types of particles which can be conserved individually so that you have stationary currents of these individual conserved species, which of course depend on the density of particles that are present on the lattice. And again, we're talking about time-dependent phenomena now, not static phenomena. So now what is it that we want to investigate in this context of universality? Well, one of the basic quantities to look at are the dynamical structure functions, which are just the stationary correlations, the time-dependent stationary correlations of the fluctuation fields. So you look at your occupation number, which is this quantity nk. So you look at the number of particles of the species alpha at site k at time t. You subtract the stationary background, and you want to study how these deviations from stationarity, how they fluctuate. So you look at the joint correlation of these two quantities at two different times, which of course depends only on the time difference because the average is taken over the stationary state. Now, from this, you can immediately get, by taking the sum of all lattices, you get the static compressibility matrix, so the stationary density covariances, because the particle number is conserved. This will not depend on time. You can also compute the current Jacobian, which is the derivative, the matrix of the stationary currents with respect to the conserved densities. We're taking the sum of all k, and also this, because of conservation law, this does not depend on time. So these are static quantities you can get immediately. But you also get the large-scale behavior if you look at large k and t, because if you then somehow manage to evaluate these functions, you get the dynamic exponent and the scaling functions that we are after. So now, of course, with interacting systems, and therefore it's not easy to compute these quantities. And one famous approach that has been applied and forwarded in particular by Herbert Spohn is nonlinear fluctuating hydrodynamics. So basically what you do is you coarse-grain these fluctuations, you look at large scales, and you expand your current density relation. And it turns out it's usually enough to expand up to second order in these fluctuation fields. Of course, will be nonlinear. Now, you also know that there's diffusion, so you add phenomenological diffusion, and you know since you have a lattice gas, there will also be noise. So what you end up with, if you go through this procedure, is a set of coupled noisy Berger equations. So here you have the time derivative of your fluctuation field, and this is the derivative of the current. And the current has these contributions. First, the linear part just comes from the drift of your fluctuations. Then here's the bilinear interaction term with the mode coupling matrices that you get from the stationary current density relation. Here's your diffusive term, and then there's your noise. And you can easily see that these coupled Burgers equations are just a set of coupled one-dimensional KBC equations, just by looking at the derivative, saying that this density field is derivative of a height function. So what I want to point out here is that this coarse-grained evolution equation is fully determined by macroscopic diffusion constants here, by the macroscopic stationary current that you get from the static behavior, and by the static compressibility, which enters the normalization of these fluctuation fields. So once we can somehow handle this equation, we can get information about the time-dependent behavior and space-dependent behavior from the static behavior. But of course, since this is a nonlinear equation, it's still not so easy how to get information from it. And one approach that has been used is mode coupling theory. So let us look at the case where all these drift velocities of the fields are different, because then these off-diagonal elements of the structure function, they will decay very quickly, and also these products of different self-couplings, and basically end up with a mode coupling equation for just the correlation of a field with itself. And the equation that we get from mode coupling theory is what you see here. The time derivative of your structure function has a linear part, which contains the diffusion and the drift. And then here the nonlinear part, which has this nonlinear memory kernel, which is quadratic in the fluctuation fields. And you have the mode coupling matrix. Now, again, we have a nonlinear equation that's not easy to solve. And of course, one can try to solve it numerically. But we managed in 2015 to actually get exact scaling solution, not general solutions, but exact scaling solutions for these equations. And what we found is the following. If all these coupling coefficients, all the line coupling coefficients that appear in the quadratic term, if they're all zero, well, then no surprise, you get Gaussian behavior, because then just have a linear problem. The dynamic exponent of such a mode is 2, and the structure function is just the Gaussian. On the other hand, if the self-coupling of a mode is non-zero, well, then you have a nonlinear part, and then dynamic exponent will be 3/2, which is what we know from KPC. And indeed, there is a case where the scaling function is this Payhover-Spohn scaling function for the KPC equation. But there's also a case, namely when you have a diffusive coupling to your nonlinear, to your quadratic mode, then there can be something different which is not really well understood. So you get a KPC or modified KPC scaling. However, there's a third case. Imagine a mode alpha, some conserved law, does not have any self-coupling, but couples to other modes, which have a non-vanishing self-coupling coefficient. Then it turns out that you get a whole series of dynamic exponents that are allowed, namely 3/2, 5/3, 8/5, 13/8, and so on, including the golden mean. And the scaling functions are just a function of a Levy distribution, of a stable Levy distribution. And if you look at these numbers carefully, then you realize that these are just the ratios of neighboring Fibonacci numbers. And these ratios were first discovered in snowflakes by Kepler in the 17th century. And therefore, we call them Kepler-Fibonacci ratios. And this whole family of universalities, we just call Fibonacci universalities, including diffusion, because also Z alpha equal to 2 has this property, namely 2 is equal to 2/1, and 1 is just the first Fibonacci number. So that's what we found, is that diffusion and KPC are just part of a big infinite series of universality classes. Now, this is, as I say, a result that rests on two assumptions which are both uncontrolled. The first assumption is that we can use nonlinear fluctuating hydrodynamics. Well, maybe one can, one can't. The second assumption is that we can use mode coupling theory, which is yet another uncontrolled assumption. So we don't really know whether it's true. So in order to find out whether this exact solution makes any sense, one still has to make simulations to compare with real systems. Now, the first type of systems that we looked at were exclusion processes, namely lattice gases, one-dimensional lattice gases that are coupled to each other. So basically, you can think of 3 one-dimensional lattices, and on each lattice particle is jump, but the rate of jump depends in some form on the neighboring sides. The way what we have chosen is just a linear dependence. So if you want to jump from, say, k to k+1, then you see that the rate of jump is somehow linearly dependent on the number of particles on the neighboring chain on the same pair of sides. So that's the type of what we are looking at. And it turns out that in these cases, one can realize many of these universality classes. So in particular, the one with the golden mean, where the dynamic cone is the golden mean, and correspondingly the scaling function is this Levy distribution, the phi stable Levy distribution. Now what you see here are simulation results, Monte Carlo simulations together with the prediction mode coupling theory, and you see that the agreement is very good. And it's actually astonishingly good, because if you zoom into this curve here at a fixed time of 3000, you basically cannot distinguish the simulation data, the black dots, from the theoretical prediction, neither near the peak nor near the tails of the distribution. The agreement is baffling.
Gunter,
so this was this particular case. So we looked at some others. We looked at, again, the same model for different parameter values, where one mode has this new 8/5 Fibonacci exponent. And again, if you look at this agreement between simulation and the fitted Levy distribution, again, the agreement is baffling. And the same for the 5/3 Fibonacci, which appears in the same model, and the 3/2 KPZ. Also here, the agreement is excellent.
Gunter, you have 2 more minutes.
Okay, good, thanks. Now we did more, and this is more recent work. We looked at the Nagel-Schreckenberg model for traffic flow, which is much more complex. There's only one conservation law. And well, since it's interacting, one might guess it belongs to KPZ. And indeed, if you look at the simulation data, again, agreement and KPZ behavior from Brehofer-Spohn is excellent. The next thing we try to find is this modified KPC. Well, we don't have any simulations yet, but at least we managed to find a model where you would expect this to be the case. These are 2 random walks, independent random walks, but again, with the rate of jump is a linear dependence on the number of piles on the other lane. And finally, yet something else. So far, we have only looked, these are all studied model systems that have conservation laws with at least 1 pile number conserved. We also looked very recently at non-conservative dynamics. Namely, we looked at an exclusion, symmetric exclusion, where you annihilate and deposit pairs of particles. So we have no conservation law. Now, this relaxes exponentially fast in time. However, if you condition the process on having a very high hopping activity, an unusually high one, then there is a phase transition line where you detect conformal invariance. This is known from a mapping to spin systems. And so you have a ballistic scaling with dynamic exponent 1, which instantly is also a ratio of enabling Fibonacci numbers. And the first 2, 1/1 is 1. And the structure function is 1/t times the Cauchy distribution. So yet another scaling function, and the 1/t comes from the fact that we're not conservative. But an observation is also that when you do this condition dynamics and you look for an equivalent dynamics where you would expect this behavior as typical behavior, you would look at a system with an effective long-range interaction. So these are our recent results, which have answered some questions about the validity of this approximation, but of course leave many questions open. And I want to mention, just to finish the talk, with these open problems. So first of all, we have this fantastic agreement between the theoretical scaling function and simulation data. Could it mean that this Levy scaling form that you get from the mode coupling theory is actually exact? Well, we don't know. So one way of looking at it would be to try to find exactly solvable models, where one can perhaps do beta ansatz to find these scaling functions, or one can try to look at mathematically rigorous results, which have been obtained by Patricia Gonçalves, with whom I'm collaborating on anharmonic chains. And one can also try to look at hydrodynamic projection, a mechanism that has been, particularly by Doyon, has been studied recently. We can also find these Fibonacci universality classes. Maybe this gives further information about whether or not this is exact. Then there's still the open question of the modified KPZ. What is it? What is the scaling function? We also have some indication that there might be universal finite time effects. So not only at late times, also at finite early times, there might be some universality. And then there's also another question, namely the phase separation, which, according to Constantia, seems to be related to complex mode velocities. But this is a connection that's still not well understood, because in this current Jacobian, you always expect real mode velocities.
Gunter,
finally,
could you please wrap up?
That's the very last point. So we found all dynamic components are 3/2 or bigger. The only one we found that's less for non-conservative dynamics to non-log interactions. Is that generic or not? That's the last question that I have. Thank you for your attention.
Okay, so since we have just very little time left, any questions? Okay, Abhishek.
So basically, I mean, what this suggests is that, mode coupling itself is an approximation to solving the fluctuating hydrodynamic equations. But what you're suggesting is the corrections to MCT are probably negligible in the scaling limit. Is that right?
This is what it looks like. Yes, right. Of course, I'm not talking about the non-universal coefficients that appear in the scaling forms. They might still be corrected by more precise calculations, but the universal scaling form seems to be exact.
Okay, thanks.
Yeah, Mustansir, please.
Hi, Gunter. Thanks for a beautiful talk. Before going to complex mode velocities, one passes through a critical line of, where we have passive scalar problems coming in, where the matrix is not diagonalizable. I mean, do you think analytic approaches can actually be applied there? I mean, fluctuating hydrodynamics and so on?
Yes, I think it is possible, except it hasn't been done yet. You see, the mode coupling equations you can set up even when the matrix is not diagonalizable. Our exact solutions, I don't know whether they still work in this case, because we do rely on the diagonalization in this treatment for the scaling functions. But you can definitely set up the equations and try to solve them numerically. And but I don't know what will come out. That's something that one should perhaps do.
Thank you.
Okay, if there are no more questions, let's move on.
Question.
Okay, please. A little bit fast,
yes.
please.
Sorry. So,
okay.
Gunter, I wanted to ask if it's very nice that you have all these different universality classes of different dynamical exponents. But suppose I wanted to go outside this class and try to find even more, then what would be the most promising direction to generalize the treatment that you have given?
I think it's really non-conservative dynamics. So you go to systems that don't have a conservation law, but still exhibit critical behavior. Then I think a lot more can happen. That's my feeling. Or to long-range interactions, in which case many of these assumptions that we use in the mode coupling theories are simply not valid. For instance, this fast decay of the cross correlations, this will not be true if your interactions are long-ranged. So these are the directions where I would look.
Thank you.
Okay, are there any more questions? Okay, if not, let's thank Gunter for a very interesting talk, and